Hi friends, welcome to my channel. Let's have a look at problem 785. Is graph bipartite? In this video, we're going to share a solution based on traversal. This video actually is a follow-up video for Leetcode problem 886. So here actually we can use essentially the same code. First, I'll read through the problem statement, and then we do the coding, and in between, we're going to explain the logic. So first, the problem statement. There is an undirected graph with n nodes, where each node is numbered between 0 and n-1. We are given a 2D array graph, where graph U is an array of nodes that node U is adjacent to. In other words, this 2D array is a node adjacent list representation of the graph. So the graph has the following properties. First, there are no self-edges. Second, there are no parallel edges. Third, the graph is undirected, or the edges are bidirectional. And fourth, the graph may not be connected. Actually, this is an important assumption. So this means that the graph is not necessarily singly connected. So a graph is bipartite if the nodes can be partitioned into two independent sets, A and B, such that every edge in the graph connects a node in set A and a node in set B. So if you examine the definition, you see there are no self-edge, and so this assumption is important, right? If there are self-edges, then for sure the graph is not bipartite. So return true if and only if it's bipartite. So here it means the graph. So let's look at the examples. So there are two examples. In the first example, it's not possible, so we return false, as explained. In example 2, so we're going to return true. So we can group 0 and 2 together, and 1 and 3 together. So with that said, let's also look at the constraint. Basically, on the number of nodes, it's bounded above by 100. So all the others are basically consistency assumptions, right? So with that said, so we're ready to do the coding. So here, the problem solving logic is that we interpret this problem as a coloring problem using two distinct colors, or you can interpret the two colors as the names of the two distinct sets A and B, right? So we're going to color the neighboring nodes with different colors. If we can finish the coloring, so we are going to return true, otherwise we return false. So in this problem, different from problem 886, so the graph is already in a node adjacency list representation, so we do not need to build this graph from scratch. Therefore, in the first step, we're going to make some preparation. So here I'm going to initialize a dictionary called color. So this color is going to track the nodes that are already colored. In the second step, we're going to write a traversal hyperfunction. So this function is going to check if a connected component is bipartite or not, right? So here, let me write this. I'm going to first write it using depth first search, and then we will make some comment or variants. So here, because I'm going to write with depth first search, I'm going to use a stack, right? So containing the source. First, let's assign a color to the source. Let's see, we use 0. So here you can interpret as this. 0 means white, just for the ease of understanding, right? 1 means black. So later, if we want to do the assignment, so we're going to use 1 minus the color of a neighbor, right? So this will be very convenient, which you will see. So next, we're going to do the standard traversal while loop, while stack. First, let's get the top node in the stack, that is stack top, right? And then we're going to check the neighbors for neighbor in graph node. So there are two possibilities. One is neighbor is already colored, and the other is the neighbor is not colored, right? If neighbor not in color, so in this case, we need to assign a color to neighbor. So we need to assign a different color, right? So neighbor will be equals 1 minus the color of the node. So which corresponds to this comment here, right? This is very convenient. So we need to also add this node neighbor to the stack. Otherwise, so if neighbor is already colored, we need to check inconsistency, right? If color of the neighbor equals color of the node. In other words, the two ends have the same color. So in this case, we are going to return false directly, right? So otherwise, we continue, and then after the while loop, we are going to return true, right? So this is the traversal help function. Let me summarize. This traversal help function determines if the connected component containing the source is bipartite or not. So next, we're going to do the problem logic and check. So problem logic and check. So this is actually very routine. So first, I'm going to track the length information. So it's not absolutely necessary to introduce this variable n. Here we introduce it here for clarity and for ease of use. So then we are going to do the iteration, right? For I in range n, right? So notice that this nodes are numbered from 0 to n minus 1. So we write range n here. And then we want to check first if I is colored or not. If it's already colored, it means the connected component containing I is already colored. So we continue, right? If I not in color, right? So we are going to do the traversal or do the work temp. So equals traverse I, right? So if not temp, it means that this connected component containing I is not bipartite. So we are going to return false directly without further check. So otherwise, after the for loop, if nothing has returned, so we're going to return true, which means that the whole graph is bipartite. So with that said, actually these three steps form a solution format. So let's first do some checks. Yeah, it passes a special case. Now let's look at the generic case. Yeah, it passes all the test cases. So here, let me copy on this traversal function. Here, because of the way we use the list, it's a stack. So if we pop here from 0, so it corresponds a queue. So this traversal will be breadth first search. Let's also test this case. So actually, typically, the breadth first search is a little bit slower when we do the test. So if that were the case, so you can actually do something like this, collections, deck. So you can use this as a deck so that we can use the deck method. Let's see, pop left. Then we can do the test. Yeah, it passes all the cases. So let me recover the original code corresponding to depth first search. Just need to use pop and test again. Yeah, I guess that's about it for this specific problem. And in this video, we first did some preparation, and then we wrote a traversal hyperfunction to check if a connected component is bipartite. And finally, we do the problem logic and check. So this provides a format of solution. So there are for sure some other variants to be which deserve further exploration. So with that said, I guess that's about it for this video. Thank you.